Welcome to Breadboarding. This is video 23 in the Breadboard 8088 PC series, and in this video we'll be looking at PC Compatibility Part 1, where we'll be adding the interrupt controller, power on self-test, the timer and the parallel port B. So in the previous video we looked in detail at what makes a microcomputer IBM PC compatible. So in this video we're going to be doing the I/O ports and interrupts to make them the same as the PC, or at least the BIOS will be configured for any differences. We're going to be adding the interrupt controller because that's needed for the keyboard and the floppy disk controller to work. And we'll also be adding the timer, the parallel port interface, port B, and the speaker so that we can actually get the power on self-test beep codes. And this is our high-level plan. You see these items are part of the plan, and the keyboard DMA controller, floppy disk, BIOS, and booting from MS-DOS will be coming up in future videos. So I've updated some of the diagrams we reviewed in the last video, and this is the system board where we've got the 8255 parallel port interface. Now in fact you can see in the green that we need here, there's very few signals we actually need here, and it's mainly to do with the timer and speaker data, and you can see down here timer, speaker data, timer, speaker data. Most of this other stuff here is all to do with configuration options and things, including things like the display type and stuff like that. But we'll see how we can replace this later. This is the timer. We're going to be adding the timer. We just need to include a divide by 2 to take the peripheral clock from about 2.4 megahertz down to 1.19, which is what the timer makes use of. We're also going to be using this design for driving a small speaker. This is the original CPU board, and we need to add the interrupt controller, but in our particular case we're going to be adding 2 interrupt controllers, and we'll look at why that is in a minute. So this is the compact Deskpro 386 schematic diagram, and this has got the keyboard controller here, and we can see here that the keyboard controller actually had the display type. So rather than having the display type on the PPI, then this was actually coming in through the keyboard controller, so that's something we can look at in some future videos. And we've also got the 2 programmable interrupt controllers here with a timer, and it's also got the replacement for port B. So rather than having an 8255, which is like a 40-pin chip, that's been replaced by a quad flip-flop and an 8-way buffer. Not all of these signals are used, as only probably half of the signals are actually used on there, but that's the design that you'll see, that the XI88 that was used by Sergei Kiselev, which is what we've been basing some of this information on, and also the BIOS which Sergei developed. So you can see here we're going to be adding the 2 interrupt controllers, and they are linked together. One of them's a primary one that drives the interrupt line to the processor. We need to include some input-output chip select logic for all the chips we're adding, plus in particular the port B write and port B read. We're going to be adding the port B logic, so this is the buffer that provides the read of port B, and then the flip-flops that provide the write. We don't have to worry about things like the non-maskable interrupts. We're going to remove that, so we don't have to worry about that. And then adding the speaker output circuit, and then also we've got the programmable timer. So let's take a quick look at the ports and the port B values we're going to be looking at. So the I/O ports. This is an enhanced version of the sheet that I showed last time. So it shows the I/O port ranges for the various items that we're adding. The ones in purple are what we're going to be adding during this current phase. So the DMA chip select, for example, the programmable interrupt controller, the programmable interval timer, port B read and write, the keyboard controller, which will probably be a couple of videos time, the power on self-test chip select, and the programmable interrupt controller too. And then there's also a floppy disk controller we'll be adding again in another couple of videos. So these are the I/O ports we're going to need to decode, so we're going to do a PLD to do that. And then this is a output of what is going to be reading from port B and what's going to be written to port B. So writing is fairly minimal. There's just the gate 2 output to the timer for controlling the speaker. The speaker data if we want to drive the speaker directly from the port there. There's a turbo option for the original XI8088 which had a faster clock mode, but we're only going to do the 4.77 megahertz standard clock. And there's also the enable the I/O checking, which again we're not going to be using. So really there's only 2 data lines on the output port that we're actually going to need to use, and then similarly on the input port, and there's a couple of other items here. So we've got the 2 outputs from the timer. Output 1 was originally the dynamic RAM refresh, and that can be used for providing timers and various other things like that. So let's have a look at the schematic diagram, which is still work in progress, but it's
got most of the features on here that we're going to be needing to get the PC booting. So this is where our processor was, and the RAM and the ROM here. This is where our monochrome display adapter card is over here that we developed. The keyboard controllers down here are legacy LED keypad and display there. But the area really which I've been adding is now this area up here. So to start with, I've laid out the DMA controller stuff because this actually needs to talk to a lot of the address bus. So over here, what we've actually got is the latches, the DMA controller, and the register that's used for providing the upper address lines. So I'm not going to go into that now, but I've laid it out there just so that we can make use of all the various shared bus signals and things. So here we've got the I/O port decoder. So this is taking the I/O signals and decoding into all those values and ranges that we showed in that spreadsheet there. Then we've got a clock PLD, which is taking some of the clock signals coming out of the system as it is and modifying these. The DMA controller actually needs a slightly different clock signal from the one that the CPU uses, so that's to do that. And the programmable interval timer needs the P clock divided by 2, so this will sort out those clock signals. Then we've got our two interrupt controllers, so these are tied together, and you can see that we've got the number 1 and number 2, so this is the primary one. And when we look at some of the outputs here, so you can see there the interrupt output there in fact goes all the way down to the CPU, whereas the interrupt for the second one actually goes into IRQ2. So the way how these are chained together is that when there's an interrupt occurring on this one, it actually causes an interrupt on here. Then we've got our timer. And the main thing the timer is used for now is actually for driving the speaker, and it can also be used for other things, but in particular we're actually using it to drive the output to the speaker here. So speaker has a simple circuit driving out of here, and there's a little bit of logic here with fairly simple gates and things to combine the outputs here. Now output 1 was originally, the timer of output 1 was originally used on the XT to refresh the dynamic RAM. Now this can still be used as a timer and can be used for doing fairly precise timing loops, but we don't need to refresh any of the RAM because it's all static. And then output 2 is used really to drive the speaker as it stands at the moment. And then at the top here, we've got the power on self-test port. So the post port basically is on port 80, and the BIOS just writes code to this, and all it really gives you is a sort of a status as the BIOS works its way through. Obviously if it stopped at some point or halted for whatever reason, then the stage where it stopped would be the post code. And then we've got the reading for the port B and the writing to the port B. So over on the left hand side here we've got our 4 flip-flops which provide the output. Primarily we're using it for the gate 2 and the driving the speaker output, and then this one provides the inputs as well. So this basically replaces the PPI 8255 chip. Okay, so I'm going to start to look at laying out the board. I will leave space for this row here. We've only really got this one here at the moment, but I'll leave the space for these ones, and then we'll look at laying out these other two, and then we'll go and assemble that. And then we probably won't have time to test it during this video, and what I will look at in the next video is configuring Sergey's XT BIOS so that it'll actually run on this breadboard PC. And what that should then allow us to do is to be able to test that and see whether or not we get anything on the power on self-test port, if we get any beeps from the speakers, and should give us sort of confidence that things are working before we start to add the other things like the DMA controller, keyboard controller, and ultimately floppy disk controller. So I've printed out the area of the schematic we're going to be laying out, and I printed it in PDF, and Acrobat Reader has the ability to print out in poster style and allows you to overlap by about ½ an inch here. So basically these are 2 A4 bits of paper glued together. Now the DMA chips down here I'm going to be plugging in, but I'm not going to really wire them up at the moment. And then this is the decoder, the 2 interrupt controllers, timer, another PLD here. And we've got the power on self-test port, and then port B, output and input. Then I've also got a small loudspeaker here that I've mounted on a bit of Breadboard, so there's just the wires there are just connected to 2 outside ones. And then we've got the other components we need and decoupling capacitors, and there's also a Breadboard Buddy Hack modular power connector there as well.
So here's the breadboard we're going to be laying this stuff out on. So I've laid them out hopefully approximately where we need them. We need to try and make sure there's a bit of a gap between the various chips, and I've tried to stay away from the end here. And we also need to put our breadboard buddy in the end here, so I'm just going to put that in. Don't want to go too close to that. So what I'm going to do now is to plug these in, wire up the power lines for everything apart from the DMA ones down the front here, and then I will wire it all in, and when we come back hopefully it'll all be ready to plug into the main computer. Just press all the chips in to make sure they're all seated properly. Then we're going to plug in the power rails. That one there is a little bit long, we'll replace it in a few minutes. One of the things I have noticed is I was running out of blue wire, which I generally use for doing control signals, chip enables, all those sorts of things, clock signals. And so what I'm doing now is using the yellow cable, because I had about 3 reels of yellow left. So that's the reason why I've changed some of the colours if you compare this with some of the other videos. Now I'm going to put in all of the decoupling capacitors. If we don't put decoupling capacitors in close to the ground rails here, then we may get some interference on the signals caused by ground bounce. So we're going to plug in those chips at the top. That's power and self-test and port B, read and write. Just going to tie those extra lines to ground or to 5 volts, which are needed before we plug in any of the wires. That's a chip enable for the power and self-test, so that's all done. So now for port B read, that needs to be plugged into the output of port B there. Plug in enable, the IO enable check, and then we need to feed the output from the timer, which is coming in from there, and the speaker output to the manual control of the speaker. The output 2 from the timer is going into the port there. Let's check those things off. So you're going to do the enables a little bit later. Now just wiring in the data lines. So there's only 4 data lines going into the right port B. Just need to put those other wires back once we've done that. Now just going to wire in those signals down to the bottom there. So that's like speaker output. So now I'm going to start wiring in the interrupt controllers. Just need to put in the links timed to ground and to 5 volts to start with before we put in any other cables in. So that's the cascade lines which allow the 2 interrupter controllers to work together. So the interrupt from the controller 2 goes into IRQ2, and then we just need to tie the interrupt acknowledges together, and that long cable there will go off to the rest of the board. Now we'll plug in the address line, so A0, and tie those 2 chips together for A0. Check those off. Now enabling the IO read, IO write together, so just wiring those in. Now I need to sort out all of the timer gate signals. So there's the outputs from the timer going into the PLD there for controlling the speaker. And the clock signals are being wired together. We do need to still feed in the clock signal from the system clock into there. Then the read and write enable, IO read, IO write also plugged in there. So now we're going to do the chip selects. That's a chip select for the interrupt controller 2. Just needed to sort a few things out there. I think I made a bit of a mistake this time. Just need to sort it all out. So yeah, that was the IO read, then we're doing the IO write there. Then that is the port B write enable. Turn it off, and then they'll just put in the port B read enable. Then the chip select for interrupt controller 1. And the chip select for the timer.
So it just took a bit of messing around to sort out the cables down the bottom there. So I haven't done the DMA ones yet. Now just do another extra interrupt line there for the timer. And now we're plugging in the speaker. So this is the output through the transistor to the speaker. And we'll just plug in the top there. Check that off. And these are just the address A0, A1 for the timer chip there. We just need to wire in the data lines. So we're just going to use these DuPont cables to wire all the data lines together, and then the last one there will have a cable going off to the main computer board. Check all that off. Okay, so I've finished hooking up the majority of that. There are still a few things we need to wire in. When we put it alongside the main board, we're still going to need to wire in the address lines, some of the I/O lines along here, and the address lines over here, just a couple of things, and then these trailing wires there, that's for the CPU interrupt and the interrupt acknowledge signals. So those are going to wire in on the diagram here. You can see they go all the way off down to the CPU here. So that's all I'm going to do for the moment. So you can see here we've got the I/O port decoding, we've done the interrupt controller, the timer, the parallel port B, and the speaker for the power on self-test, and we've also done the power on self-test port as well. So we've got all the things there really that we need to start to try out a BIOS. So in the next video what I'm going to do is looking at using one of the XI8088 BIOS configurations, modify that to work with the breadboard PC, and we'll see whether or not we can get the BIOS to power on, and if we can get anything on the video controller, and if we get any beats power on self-test codes. If you don't want to miss out on future videos, please hit subscribe, and if you can hit like as well, it just helps to make the videos available to a wider number of people. Thanks for watching.